Well, hey everyone, welcome back to the bench. Today I'm going to talk about how to select the proper resistance value for your LED circuit. I'm going to be mainly concerned with these low power LEDs. A higher power LED you might want to use a driver for. But if money is no object, you could use a driver for these, but normally it would be better just to use a resistor. It's a very simple circuit. So how do you select the resistance value? Well, you need to know a couple parameters of your LED. One parameter is its current rating. If you look at the data sheet, there'll be a maximum continuous current. You normally don't want to exceed that because you can decrease the life of the LED. And if you grossly exceed the current, you can actually burn the LED out. The other parameter is the forward voltage. Well, with a single die LED, with the indium gallium nitride type, which are the blue, white, and bright greens, typically the forward voltage is around 3 volts. It does depend on current, but at normal operating currents, the forward voltage will be around 3 volts. Now, if you have the lime green, yellow, amber, orange, or red types, those have a typical forward voltage of around 2 volts, give or take. Okay, here's our sample circuit. We have our supply voltage, the resistor we're going to figure the value of, the LED itself, and ground. You can think of this as a ladder of voltage drops. Starting at ground or 0, you climb up higher, voltage drop of the LED, then the voltage drop of the resistor plus the LED, which brings us up to the supply voltage. Another important thing to understand is that the current is going to be the same in each part of the circuit. The current flowing through the resistor is going to be the same as the current flowing through the wire and the LED. So how do you figure the value of this resistor? Well, it's quite simple. You just take the supply voltage minus the forward voltage drop of your LED and divide it by the current that's going through the circuit. So to make an example, let's say we have a supply voltage of 5 volts. We're using a blue LED which has a forward voltage drop of 3 volts, and we want to put 20 milliamps through the LED. Well, we put in the formula here and we get 100 ohms. So what I did, I set up a circuit in this bright eye-blinding blue LED. That's a 100 ohm resistor, and I measured it previously. This is the voltage across that resistor. Came out very close to 2 volts, and that's what we used here. 5 minus 3 is 2 volts across that resistor, with 20 milliamps giving us 100 ohms. The next thing you need to figure out is the power rating of your resistor. Resistors come in 1/8 watt, 1/4 watt, 1/2 watt, and so forth. So you can take I squared times R, or the current times the resistance, and that'll give you the power that's going to be dissipated in the circuit. So we had 20 milliamps squared times 100 ohms, 40 milliwatts. Well, 1/8 of a watt is 125 milliwatts, so this is way below that. The circuit does not use much power. So how much is the total power of the circuit? Well, it's going to be the current through the circuit times the total voltage across the circuit. So it's going to be 20 milliamps times 5 volts, or 100 milliwatts. Now we'll take a look at powering more than one LED in the circuit, and how do you figure the resistor value? Now there's a right way of doing it and a wrong way of doing it, and we'll look at why that is so momentarily. But there can be a situation where this is okay, and we'll take a look at that a little later as well. Well, you might have figured it out already that it's the sum of the forward drops of the LEDs that we put in our equation. And that's where I said look at this as a ladder of voltage potential, starting from 0, and you go up across this LED, then you have another LED yet, then your resistor, and the sum of all that is your supply voltage. So yeah, it's pretty much the same equation, except you have to have the sum of the two forward voltage drops of your LEDs. So using a similar situation, but of course we need a higher supply voltage, and I'll use 9 volts in this case. So we have 9 minus 6, and we'll use the same current value of 20 milliamps. That gives us a resistance of 150 ohms. And using these formulas, the power dissipated by a resistor will be 60 milliwatts, and the total power dissipated by this circuit will be 180 milliwatts. Now if we had the same exact values, supply voltage and LEDs, this is why putting them in parallel would not be a good idea. It really wouldn't be an issue of evenly dividing the current. Good quality LEDs will split the current pretty evenly. In fact, a lot of those chip-on-board arrays, that's how they're set up, with series parallel circuits of LEDs. But not to get off track, if you want 20 milliamps in this LED and 20 milliamps in this one, well, you're going to have 40 milliamps because the current's got to split for each LED. So now a resistor will have 40 milliamps going through it. So we'll use this formula here, same as this one here. Because these are in parallel with each other, the voltage drop is only going to be 3 volts across this part of the circuit, because we're using the two 3-volt LEDs. But we're splitting the current, so we have to add the currents together. So it's exactly same equation, we just have to get our numbers correct. And we end up with 150 ohms. Why is it the same as this? Well, we're doubling the current and doubling the voltage drop. That's why. So it works out to be the same resistance. But look what happens. The power resistor dissipation is 240 milliwatts now, 4 times what it was in this circuit. The total power dissipation of the circuit is 360 milliwatts, which is double of this. So we're making the two LEDs light up, the same brightness, same current as this circuit, but we're wasting so much more energy. So that's why this design is bad. Now, where can this be good? If we didn't have high enough supply voltage. If this were only 5 volts, well, putting these in parallel means we only drop 3 volts across this part of our circuit, and that'd leave us 2 volts to drop here. So you can do the calculation and figure out what the resistor value would be here. Well, I hope this made some sense to you and is of some use. That's it for today. Thanks for watching.